In this video, we are going to look at how to simplify Boolean expressions. Before watching this video, you need to have an understanding of Boolean logic gates. So why should we simplify Boolean algebra? It's important to simplify expressions because gates cost money in the real world. By using less gates, we can save more money. And by simplifying the expressions, we will be using less gates. Now, we can simplify an expression and prove simplification by using a truth table. Let's prove this by looking at the following expression, a and b in brackets, or a. Here we have the first part of the truth table showing. We can see the inputs a and b, and then we can see the results of having a and b in the third column over here. Now we're looking at the full expression. You can see the results in this final column over here. Notice how the results are actually the same as the values under the A column. This means that A and B, or A, is just the same thing as saying A. So we'll be saving on two gates by just simply having A instead of that full expression. Now, in order to simplify Boolean expressions, there are some laws that we have to know about in order to help us. Just a warning here, there are 8 laws and they can be confusing to understand at times. So you may want to replay this video a few times until you understand them. I'm going to list their names first, then we'll look at them in more detail after. It's helpful to know the names as the names make it easier to remember the law. First we have Identity Law, then Dominance Law, then Idempotence Law, Distributive Law, Associative Law, Commutative Law, Absorption Law, and finally De Morgan's Law. An easy way to remember this is, in this order, the first letters make the sentence, I did a CAD. Yeah, this doesn't make much sense, but welcome to computer science. Alright, starting with the identity law. Here's 2 examples using both and or gates. You can see that the resulting output takes the identity of A when we have A and 1 or A or 1. To explain this, when we have A and 1, the 1 is always true. So therefore the output will always be impacted by whatever A is. If A is false, the output is false. A is true, the output is true. With the OR gate, 0 is always false. So whatever the value of A is here will impact the output. Pause the video here and prove this with a truth table. The dominance law allows the 0 or the 1 to take dominance over the other output. If we have A and 0, we don't put the value of A because 0 is always false, we always get a false output. The same with A or 1. No matter the value of A, 1 is always true, so we'll always have a true value with an OR gate. Pause the video here and prove this with a truth table. Idempotence or idempotence, doesn't matter how you choose to pronounce it. I won't judge you most of the time. In the simplest way, this word suggests a value that remains the same. Looking at these 2 examples, this makes sense. A and A will only ever be the value of A. The same for an OR gate. So when you see 2 A's in an expression, you can remove one. Pause the video here and create a truth table to prove this. Distributive law is a little confusing, but essentially the idea is that the multiplication, the AND gate, of 2 values followed by the addition of another value is the same as multiplying the result of the individual value being added to the other values. In this case, AND gates are multiplication and OR gates are addition. Here are the 2 examples. Pause the video here to create a truth table to prove this. That explanation may have been quite confusing to understand, but if you examine it with a truth table and just really look at what I've said, consider replaying it. It will make more sense. The associative law is one that looks confusing, but actually makes a lot of sense. Here's the two examples with and or gates. The idea is you can move the brackets and still have the equivalent expression. To make this make sense, think about basic mathematics. A plus B plus C gives the exact same answer no matter where the brackets are placed. Pause the video here and create a truth table to prove this. The commutative law is the law where you can swap values around and still have an equivalent expression. So A and B is the same as B and A. And the same with A or B is the same as B or A. Pause the video here to create a truth table to prove this. The absorption law essentially is the law that shows that when you have situations like these, the input which appears most frequently is the value you can simplify down to. This makes sense with the AND gate example because no matter what the value of B is, as long as A is true, you get a true output. In the OR gate example, it's the same situation where no matter what B is, as long as A is true, you get a true output. Pause the video here and create a truth table to demonstrate this. Finally, we have De Morgan's law, introduced by Augustus De Morgan. Without going into too much detail, here are two examples. Now, to help you remember De Morgan's law, you just need to remember this quote. Break the line, change the sign. In the first example, where we have A NAND B, this is the same as saying not A or not B. We break the line, then change the sign from an AND into an OR. Pause the video here to create a truth table to prove this. Okay, I may have lied slightly at the start. There is one more law, but it's one you'll naturally remember. That's why I didn't say it before. It's called the double complement law. It is just a rule which states that a double negative cancels itself out. So for example, here we have not A. We actually just have A. That's the end of this video. Right now, we've only gone over the rules. After some practice of putting the rules in place, you'll be able to understand more about how they work. Have some patience with this, as simplifying Boolean expressions can be a little complicated, particularly at the start, as there's so many rules to remember. Try and make it your goal to memorize these rules. Some of them will come naturally to you, others may take a little bit of time, but just have some patience.